Hello, everybody. Welcome in results 3 now. You're going to listen to the presentation FrozenCache. Maybe some of you have seen 2 years ago Joseph Applebaum presenting the cold boot attack at this conference. And today, which made your encrypted laptops more insecure or less secure than you hoped. And today you might see a remedy which is presented by our speaker Juergen Pabel, and I ask you to welcome him.
Well, thank you for being here. I know I have a tough competition with the hacker. I think I'll be fairly quick, so if you want to go over and okay. So I think we'll probably be through in a little bit over half an hour. And if you have questions, we've got plenty of time for that. So, I work as a security consultant, and I have a blog from work which has lots of different topics that I write about, not fairly frequently, but every now and then. And also, I'm going to start my personal blog, whenever there's time. So, first, I'm going to talk a little bit about what the cold boot attacks are, just to refresh your memory. Then I'm going to talk about what the FrozenCache approach is, what it does, what it doesn't do. I'm going to give you a demo, which is going to be really impressive because you're going to see a really slow computer. And then there will be little messy details, which I'm going to skip over in the beginning just to get the point across. And then there's time for questions. So the cold boot attacks, they discovered that when you turn off a computer, that your memory doesn't go blank immediately, but rather the data is kept for seconds or even minutes if you cool it down. And in the aftermath of this research, they discovered that there was a paper from IBM which had also discovered the same fact a couple of years ago. But nonetheless, this was the first research. Okay, so that was the research that tied the combination from accessing RAM contents to forming an attack that impacts the security of full-disk encryption software. Okay, so now I have 3 mics and so that was 2 years ago here, and also 2 years ago I watched a presentation by Peter Stooch who talked about the core boot, which is a Linux implementation for a BIOS replacement. And he mentioned something about the initialization of hardware, where they had problems initializing the memory controller, and that this code is very hardware dependent and needs to be adapted for every single controller, and that was a huge effort to custom create assembly code for every single make and model out there. So they were looking for something to make it easier on them. And what they then found was this cache as RAM mode, as it's sort of known on AMD, and known as no-fill mode on Intel CPUs, which allows you to use the cache just as you would usually, but in this mode, the cache doesn't go back into memory. So what they were then able to do is implement their programs, their initialization routines using the cache, so they had a lot more room to implement their logic to initialize the memory controller, and had a lot less worries to implement this. So the idea was then to take this mode and apply it to the as a solution to the cold boot problem, and to essentially not keep the cryptographic data in memory anymore, but to move it on the chip on the CPU, so that if you extracted the RAM, you don't get the cryptographic keys. and extracting the contents from the cache isn't that easy because there's no real interface that you can ask a CPU to, get out the data. And even if you were able to do that, once you lose power to the CPU and you reapply power to it, the initialization of the CPU will clear the cache internally, something that memory RAM doesn't do itself. So, like I said, we're going to skip over some details, and I want you to think about caching as a sort of two-task thing. One is loading data into the cache. Usually it will be something where it'll be fetched from memory into the cache, and the second part is then getting the memory, the contents from the cache to the RAM. And for the purpose of this talk, it's most easiest if you think about it as two different tasks that the cache does. And also, we're going to just focus on a single CPU system for now, and even more precisely with a system that only has a single CPU, so no hyper-threading or anything. And I'll get into the details what that means with multi-CPU systems at the end. So, important to know is that CPUs nowadays, they have two levels of cache commonly on the CPU, level 1 cache and level 2 cache. Level 1 cache is extremely fast, usually at clock speed of the CPU, and it's divided usually into an instruction cache and a data cache, whereas the level 2 cache is combined, and any data that's in there could be data that's executed as code or data that's interpreted as data, whereas in the level 1 cache it'll be split up. Okay, is this an execution instruction or is it data? A little side note, in most CPUs, the level 1 cache, the instructions are already decoded. So if you have the assembly, the machine code instruction, in level 1 cache, usually it's already extracted, so the CPU doesn't have to go through the decoding stuff again. But that's just a little tidbit of information on the side. So on x86, and this is mostly for 32 and 64-bit modes the same, you have a control register, 00, which has a couple of bits that indicate the cache operating mode. The one flag is CD cache disable. When you activate this bit, it's essentially the part that prevents data from being loaded into the cache. Whereas the other bit, not write through, is more or less a bit that manages how data will then be pushed out of the cache back into RAM. That's not entirely correct, but let's leave it at that for now. There's also other mechanisms on the platform that can manage how caching behaves on the system. And the first one are the memory type range registers, and they are used to set up specific memory regions for things like graphic card memory, so that any changes to memory regions that are then represented through the graphic card, that those don't get cached, so you get the immediate update on the display. And then there's the page attribute table, which allows for individual pages to be marked as cacheable or non-cacheable. An interesting differentiation is that MTR acts on physical address ranges. So this is really the address that essentially gets sent down to the memory controller to indicate the specific cell that holds that data. Whereas the PAT operates on the linear address ranges, which is practical for operating systems to indicate certain ranges that the operating system deems cache-worthy. And then there's different types of memory with respect to cacheability, and these range from entirely uncacheable, meaning any changes to it will immediately get propagated down to memory, to something like fully cacheable in terms of it can be held as long as possible in the cache, and whenever there's a need to push it out into RAM, it'll be done. So when you want to activate the no-fill mode, all you have to do essentially is flip 2 bits, the cache disable and the not write-through bit, and we have the assembly instructions up here. From what I said in the beginning, activating the cache disable bit prevents the data from being pulled into the cache, whereas the not write-through bit prevents it from being pushed out to the memory again. Turns out this not write-through bit is not really supported anymore. So essentially it comes down to a single bit, the cache disable bit, and the various combinations that you can have with 2 bits, they are documented in the Intel's software development manual. And like I said, the setting of both bits is no longer supported. I think it was Pentium 3 or 4 when that was discontinued. So when you actually turn on a CPU nowadays, when it powers up, the no-fill mode is what the CPU will operate in until the mode of operation is changed by the software. And there are lots of different minor aspects that vary across CPU models. So the basic behavior in terms of how data remains in the cache or gets evicted, written back to memory, are more or less the same. But side effects could be something like when I have this no-fill mode activated and want to know about caching statistics. How much data has the cache held, how much hits have been done to the cache, or how many misses have occurred. That varies a lot depending on what specific CPU you have. So just starting from that, we'll get to it a little bit later, but that turns out to be a little difficult to handle in a generic way to assure that the initial goal, keeping data in the cache, is actually accomplished or not. So it makes it harder to verify. So when you have the frozen cache mode, what you want to do is you want to switch from normal operation in terms of your system is up and running into frozen cache mode, where all your sensitive data is pulled into the cache and removed from memory. So what you do is you take that data, load it into a CPU register, then overwrite the data in memory, make sure that that write actually gets sent down to the memory, so that data is no longer present in memory, and then you freeze the CPU and then write the data into the CPU cache so that they now exist there. And for as long as the CPU cache doesn't decide to then flush this data back out into memory, then you don't have the actual values in memory. So what's important, of course, to this mode is that you really can rely on these attributes. You don't want to activate this mode and then turns out, hey, my data does end up in memory anyhow. So the first part is I need to configure the initialization so that the data is altogether in cache, and then you have to make sure that it doesn't, incidentally get written back into memory later on. So what data do we need to protect? When we look at full-disk encryption, obviously the encryption key, and everybody knows about the AES keys, 128 bits, or bigger, and what's commonly used is the FIPS 197 setup procedure, so to say, which derives a specific encryption and a specific decryption key from the 128-bit that you have initially. And then there's also the key schedule, which are derived keys that are used in the encryption and decryption calculations. And of course you have intermediary data,